Hello. We are going to solve this circuit here using KCL and KVL. KCL, or Kirchhoff's current law, states that the summation of the current entering a node must be equal to the summation of the current exiting a node, while KVL states that the Kirchhoff's voltage law states that all voltage drops and rises must equal to 0 in a single loop. So okay, cut mo muna. Pa-analyze this circuit. As you can see, there are 3 loops. Loop 1, loop 2, and loop 3. And there are 1, 2, 3, 4, 5. 5 wires. So the current coming from the battery would be here, I1. These 2 wires are in parallel, so they will have different currents, I2 and I3. And this here are 2 different wires in parallel once again, so this would be I5 and I4 down here and to the right. Right? Pause. So we need to come up equations that will satisfy the KCL and the KVL, which is we are going to take the summation of the current at junction A, which is I1. I1 is entering, and it should equal the currents that are exiting, which are I2 and I3. The same goes for here, junction B. This is at junction A. And with junction B, I3 is entering. I3. And I4 and I5 are exiting. So these are the equations that satisfy Kirchhoff's current law. Next up is the KVL equations, which are determined by analyzing the loop. So starting from this point here, from on loop 1, go up here, it's a voltage rise. The voltage rise 5 volts. Then current 1 is flowing through here to resistor 1, which is equal to 4 ohms, and by Ohm's law, V equals IR, so the voltage drop here would be equal to I1 times 4 ohms, which is the resistance, or 4I1. And down here is I2. I2 is going to cross the resistor 4 ohms, so minus 4I2 and minus 8I2, which it crosses a resistance of 8 ohms, and all of that should be equal to 0. This is at loop 1. So at loop 2, we're going to start from here, opposite to the direction of the current. That's why it's going to be positive, because whenever you're analyzing and the load is the same direction as the current, it should result in a voltage drop, because it sucks voltage. Yeah, it does suck voltage. So if you go in reverse, technically it will gain voltage from down here to up here, because it hasn't crossed the load yet. So this will be positive, which means this will be 8R2 positive plus, which is opposite once again, 4R2, which is going to be negative because the current's the same direction of the load, minus 10R3, and finally minus 4I4. All that will be equal to 0. This is the KVL equation of loop 2. So we are now going to make the KVL equation at loop 3. start from here, going up, opposite of the current, which is going to result in a positive value for I4. And going through here, I5, it'll be minus 2I5, and once again minus 2I5. Because it's a 2-ohm resistor, it will be equal to 0, and this is the KVL equation at loop number 3. So from these 5 equations, we have 5 anodes, which is I1, I2, I2, I1, I2, I3, I4, and I5. So need to find a way how to solve this. The best way I have thought about is substitution. So from here, you could simplify equation number 1, equation number 2, number 3, number 4, and number 5. We could simplify equation number 5 to deduce that 4I4 minus 2I5 minus 2I5 negative 4I5 at both sides 4I5. We have deduced that I4 and I5 are equal. So now we know that I4 is equal to I5. We would substitute it in equation number 2, which is I3. I3 is equal to I4 plus I5, substituting it, and you would get 2I4. So I4 would be equal to 1/2 I3. And substituting this value into equation number 4, you would get 8R2 plus 4R2 is 12R2 minus 10R3 minus 4 I4 is equal to 1/2 R3 is equal to 0. So 12R2 minus 10R3 minus 4 times 1/2 R3. So you would get 12R2 minus 12R3 is equal to 0. So how convenient that R2 is equal to R3. You have that relation now. So we have these two relations, I2 is equal to I3, I4 is equal to I5. We can now substitute I2 into I3 in equation number 1. So I1 would be equal to 2, I2 is equal to I3, so that will be I3 plus I3, 2I3. So I will 2I3. So let's substitute this into equation number 3, which is 5 minus 4I1 minus 4I2 plus 12I2. Sorry, 8. 8. So is equal to 0. So you get 5 minus 4I1, 4I1 minus 12I2 is equal to 0. Since I1 is equal to 2I3 or 2I2, some say, we could substitute I1 here for 2I2. Sounds about right. So if you substitute I1 there for 2I2, you would get 5 minus 8I2 minus 12I2 is equal to 0. So you get 20I2, transpose it to the other side, is equal to 5. So the value of I2 is 5 over 20, or in decimal it'd be 0.25 amperes. Okay, so we now have the value for I2, which is 0.25 amps. And we also know that I2 is equal to I3, so I3 is also 0.25 amps. And we know that I1 is equal to 2 I2, which is 0.25. 2 times 0.25, you will get 0.5 amperes. And okay, awesome. And in order to get I4, 8R2. Mali! There's a correction here. This should not be R2. This should be I2 and I3. Okay. Don't be sure. So we know that I2 is equal to I3, so we could add these terms together. We get 8 plus 4 is 12, minus 10 is 2. So you would get 2 I2, which would be equal to negative 4. It should be equal to 4 I4. So I2 is 0.25, 0.25 divided by 4 is equal to I4, which is equal to 0.125 amps. And we know that I4 is equal to I5 as well, so it will be 0.125 amps, 0.125 amps. Right? Alright, we're now going to use Ohm's law in order to get the voltage across each resistor. So the voltage across R1 will be equal to the current I1 times R1. So I1 is 0.5 amps and R1 is 4 ohms. So the voltage across 1 would be equal to 3 volts. No, sorry, 2 volts. 2 volts. So the voltage across here would be 2 volts. So there's a voltage drop of 2 volts here. Since it's 5 volts here, you get here 3 volts. So there's 3 volts going here and going there, since they are in parallel. Awesome. So we know that the voltage here is now 3 volts. In order to get the voltage across R2, you get V2 is equal to the current I2, which is 0.25 amps, multiplied by 4 ohms, which is equal to 1 volt. Yes, 1 volt. And the voltage across R3 equal to I2, 0.25 amps, multiplied by 8 ohms, in which you will get 2 volts. So the voltage across here is 1 volt, the voltage across here is 2 volts. So 3 volts minus 1 volt minus 2 volts, we get here with a potential of 0 volts, which is correct because there's nothing left. So in order to get the voltage across resistor number 4, you would get I3, which is also 0.25 amps, multiplied by 10 ohms, which you will get 2.5 volts. 5 volts to 3 volts, 2.5 volts, there's only 0.5 volts left in each parallel circuit. So the voltage across resistor number 5, it would be I4, which is 0.125 amps multiplied by 4 ohms, which is exactly 0.5 volts. So 0.5 here, then it will reach here with a potential of, once again, 0 volts, which makes it correct. So voltage across resistor 6 would be the current I5, which is, once again, 0.125 amps multiplied by 2 ohms, equal to 0.25 volts. So here, 0.25 volts. And finally, the voltage across resistor number 7 would be 0.125 amps, I5 times 2 ohms once again, resulting in 0.25 volts potential difference. Volts. And if you add these two together, from here, there's 0.5 volts here, minus 0.25, minus 0.25 once again. If you reach here, you would get, once again, 0 volts, proving it to be correct.